Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Bismillahirrahmanirrahim. Let's start part 2 of our chapter number 7, that is stress transformation. Okay, so in our previous lecture we discussed the transform stress, that is sigma x dash, sigma y dash and tau of x dash y dash. We can also write them as shown in equation 1, 2 as well. Now we will move further toward a new topic, that is principal stress. These equations are also written over here, that is sigma x dash, sigma y dash and tau of x dash y dash, and you are familiar with this equation. So what if we take this equation and rearrange them, that is sigma x dash, and you take this term and move to the left side. So that sigma x dash minus sigma x plus sigma y divided by 2. Clear? And that will be equal to sigma x minus sigma y divided by 2 into cos of 2 theta plus tau of xy sine of 2 theta. Clear? And if you rewrite this equation here, tau of x dash y dash is equal to sigma x minus sigma y divided by 2 into sine of 2 theta plus tau of xy into cos of 2 theta. Clear? Now you have two equations, one is this one and one is this one. Clear? And if you take the square on both sides of this equation, for example, if you take square and you also take the square, you will get the equation like that. And similarly, if you take the square of this equation, that is equal to, and you take the square of these two equations. Clear? And add these two. For example, this is equation A and this is equation B. So if you add them, adding A and B will give you sigma x dash minus sigma x minus sigma y divided by 2 whole square plus tau of x dash y dash whole square. And if you simplify, take the square of this term, a plus b, for example this is a and this is b, and similarly you have this term and you take the square root and you add them, so you will get here the term that is sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. So you will get this. Clear? And now if remember that this sigma x minus sigma y, sorry, this is not minus sigma x, this is sigma plus y. So sigma x plus y. Now you know that sigma x plus sigma y divided by 2 is equal to sigma average. So we have to replace this with this sigma average, so that will be equal to sigma x dash minus sigma average whole square plus tau of x dash y dash whole square is equal to, let this term is r square, and r square will be equal to sigma x minus sigma y divided by 2 whole square plus tau of xy whole square, and we replace this term with r square. Now you can see this is just like equation of circle. If you recall, the equation of circle is x minus h whole square plus y minus k whole square is equal to r square. So if you compare these two equations, this equation and this equation, so this sigma x dash is actually the x coordinate, sigma average is equal to h. H will be equal to sigma average, where tau of x dash y dash minus, there is no term, so k will be equal to 0. So, and r is the radius of circle, radius of circle. So center of this circle will be h comma k. So in this, from this equation, it will be equal to sigma average comma 0. So the center of circle will be sigma average comma 0. R square is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. Clear? So basically this equation and this equation, these are the parametric equations of the circle. So the previous equations are combined to yield parametric equation of circle. That is, you can see this equation is written over here. This is the equation, sigma x dash minus sigma y whole square plus tau of xy dash whole square is equal to r square. So this is the equation. Now you can see that if you have center which is sigma average, so if this is the center, and how you will find it, you will take sigma average is equal to sigma x plus sigma y divided by 2. So you will get a center. So at center you will draw a circle of radius r, and this r is equal to, this r square was equal to sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. So if you want to find the r, so r will be equal to sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. So you can draw the circle as well. Clear? So each point of the circle will represent the state of stress. Again, this x axis represent the normal stresses. You can plot the normal stresses on x direction, while shear stress is plot on y axis. Clear? And this is the origin. So if you want to plot any point on x axis, so at this axis there will be normal stress, but there will be no shear stress. Similarly, on this axis there will be no normal stress, but there will be the shear stress. So again, this is you will get a circle when you plot this point, so you will get a circle. Clear? Now these points are, every point on the circle will show you the transform stress. Clear? So for example, if this is the point, so you can see on this point there will be a normal stress as well as, and there will be a shear stress. So if you rotate the element through angle theta, so stress will transform, and you can plot them, and it will be the parametric equation, means this point will lie on the circle. So what we conclude, that if you have a plane stress problem, clear, sigma x, sigma y and tau of xy, this is tau of xy, and if you rotate this coordinate system, or if you rotate this element through angle theta, so you will get the transform stress. So if you increase the theta, so stress will transform. So at every angle the stress will transform. Now when you will do this thing, so you will experience that at certain theta angle the stress will be maximum, and this will, you can see by this circle. So this is the, at this point A, stress is maximum. which is equal to sigma A. So after that point there is no stress, because the circle will experience only maximum stress is sigma A, and the similar normal stress, this is normal stress, and the circle, the minimum stress, normal stress that this element is experiencing is sigma B. So sigma B will be equal to minimum stress. So you can see as these point A and B lie on x-axis, and this x-axis define only normal stress and there is no shear stress. Therefore these stresses are known as principal stresses. This sigma A and sigma B are called as principal stresses. Clear? Because principal stresses are the maximum stresses, principal stresses are the maximum stresses, and in this plane where these principal stresses are occurring, these are known as principal plane. So the theta at which we get sigma A and sigma B, for example principal stresses, so this theta is known as principal plane. We will also discuss how you will find the principal plane, but remember that at this axis the two stresses, that is sigma A and sigma B, are principal stresses. Clear? Now you can see at point D we can have a maximum shear stress. We can also have a shear stress at this point, but this is less than at point D. So at point D we experience a maximum shear stress. Now this is known as maximum shear stress. Clear? But we have already discussed that at point where there is maximum or principal stress occurs, so there will be no shear stress. But in this case the shear stress is maximum, but it will also have a normal stress at point C. So this normal stress at point C is actually sigma average. I hope it's clear to you now. Clear? So principal stresses occur on the principal plane of stress with zero shearing stress. So how you will find, for finding the principal stresses without using the Mohr circle, you must know the principal plane. Once you know the principal plane or the angle at which we can get the maximum normal stresses, so you can find them by using the transform equation. So how you will find the maximum principal stress? So maximum principal stress is only theta p will exist when tau of x dash y dash will be equal to 0. Clear? So if you put tau of x dash y dash is equal to 0 in this equation, clear? So you will have this sigma x minus sigma y divided by 2 into sine of theta will be equal to tau of xy cos of 2 theta. Similarly, sine theta over cos theta will be equal to tangent of 2 theta. I forget to place 2 theta. Is equal to tau of xy divided by 2 multiplied by tau of xy divided by sigma x minus sigma y. So this is this theta will be equal to theta p. So I have derived this formula. You can also see it here. So the theta p will be tangent of 2 theta p can be found by taking tau of xy dash is equal to 0 in this equation. Clear? So you will get the tangent of 2 theta p is equal to 2 tau of xy divided by sigma x minus sigma y. Clear? So you have to put the value of sigma x, sigma y and tau of xy, so you will get 2 theta p. Clear? So 2 theta p will be some value. Clear? Now we will also see that how you can find the maximum stress, so at point A and point B. So at point A, if I zoom it, so you can see at point A, I will change the marker color. So at point A, sigma A, that is equal to OA. Clear? So and this OA is equal to OC plus CA. Now OC is this distance, and this OC is sigma average because the center is sigma average. So sigma average, and this CA is the radius. So this will be R. So sigma A is maximum stress, clear, and that is equal to sigma average plus R. Similarly, sigma B, sigma at point this B is equal to OB, and this OB is equal to OC minus CB. OC minus CB. So this will be the OB. Clear? And this OC is what? This OC is sigma average, and this CB is the radius, so minus R. Clear? So sigma B is actually sigma minimum. So you can see sigma max is equal to sigma average plus R, and sigma minimum is equal to sigma average minus R. So we can I can write this equation as sigma max comma sigma minimum is equal to sigma average plus minus R. Clear? So this is how we can find the maximum and minimum stress, which is given over here. So this is sigma average. Sigma average is equal to sigma x plus sigma y divided by 2. Clear? And this R is equal to sigma x minus sigma y divided by 2 whole square plus top y xy whole square under the root. So this equation is basically this. If you put the value of sigma average and R, so you will get this equation. Clear? So in this slide we have discussed how to find the principal plane. Principal plane are those plane at which there is no shear stress. Clear? And there will be the maximum normal stresses. How you can find that principal plane? So principal plane can be found by using this equation. Tangent of 2 theta p is equal to 2 tau of xy divided by sigma x minus sigma y. And sigma max and sigma minimum can be found if you put the sigma x, sigma y and tau of xy value in this equation. So you will get sigma x and sigma max and sigma minimum. Now you can see this theta p will be certain angle, and this will be there will be two angle, 2 theta p1 and 2 theta p2. Also, one thing you should remember that when you are dealing with the Mohr circle, so the angle which you will take in Mohr circle will be 2 theta p, while the angle which you are presenting over the element will be a angle that is theta p. So if I write over here, I will again repeat that if you are dealing with Mohr circle, so the angle which you will take is 2 theta p. I will also show you the reason. And while you are taking on the element, so you will take only theta. Clear? So this is if you are dealing with that will be 2 theta p1, 2 theta p2, and if you are dealing with this, so it will be theta p1 and theta p2. Why theta p1 and why theta p2? So now you can see this was the original x and y. So if you rotate the element to an angle of theta p, so this will be the transform axis x dash there, and this will be also transform axis y dash. So now the normal stress on this face will be sigma max there, and minimum stresses will be this one. Also we have said that when you have principal plane, so on principal plane you have sigma max and sigma minimum, and there will be no shear force, so you can draw the transform section like this. Clear? Remember, it is very necessary to draw this transform figure because you have been asked to find out the principal plane and the principal stresses, and also to draw them in a transformed manner. Clear? Okay, So now we will talk about why to take 2 theta p1 or 2, why we take 2 theta in this and in single theta over here. Also why there will be two angles, 2 theta p1, 2 theta p2 or theta p1 and p2. So you can see if you put the value of theta p like this, so this will be theta p1. But if you take this angle, this will be equal to theta p2. So if you rotate the element in this, either in this much, or if you take it theta p2, which is equal to 90 plus theta p1. Theta p2 will be equal to 90 plus theta 1. It will give you the same normal stresses or principal stresses, sigma max and sigma minimum. Also here you can see that the angle here, this angle is 2 theta p1. Clear? So why? Because you can see here one normal stress and other normal stress are at a degree of 90 degree. Clear? And here you can see on Mohr circle, this is normal stress or principal stress sigma A and sigma B. They are at a 180 degree apart. So on Mohr circle we shows double angle than in the real. So when you calculate or when you deal with any problem related with Mohr circle, we will use it in our next topic about Mohr circle. So you will see that whenever you take angle, it will be 2 theta p, and when you draw it to show the transform section, so this angle will be divided by 2. I hope it is clear to you now. Now, up till now we have discussed the principal stresses, that is at point A and point B. So at point A, this stress is maximum stress, and at point B, this stress is minimum stress. And this plane is known as where there are principal stresses and there is no shear stress. So this plane is known as principal plane. Now I have also told you that if you look at this circle, so you can also find that at this point D, the shear stress will be maximum 1. Below this point, the shear stress will be there, but it will be less than this maximum. So this maximum, at this point we can see the shear tau maximum, the first element is the normal stress, because this, if you look at the coordinate of this, so first element is x, which is this point C, and this is sigma average. So at this point D, normal stress is sigma average and shear stress will be tau max. Clear? Because this is point, at this point there is a normal stress sigma average and shear stress will be maximum. Clear? And this shear stress maximum is actually equal to CD from this circle. This is equal to CD and this is equal to R. And you know the value of R. This R is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. Clear? So this is how we can find the maximum shear stress in an element, transform element, or you can see this. Now at this point the normal stress will be equal to sigma dash will be equal to, or transform sigma x dash will be equal to sigma average. Clear? Now you can also see that at this point the shear stress is maximum. So how you will find the plane theta s, or the angle which when we rotate the element, it will give you the maximum shear stress. So we are interested to find out the theta angle for which the shear stress comes out to be maximum. So what we for this we will use the formula, that is this one. So look at this formula. So you can see this formula, this the first one, this formula, sorry, again this formula. So if you look at this formula, so you take this formula, sigma x dash is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cos of 2 theta plus tau of xy sine of 2 theta. Now we have found that at sigma, at this point D, so the normal stress will be sigma average. Clear? So transform sigma x dash will be equal to sigma average. So if I go back to this slide, so if I replace this sigma with sigma average, so this will be equal to sigma, okay, let me delete something so that you can easily understand. I will need some space. I think it's sufficient now. Okay, so if I put this sigma x dash as sigma average, and you know sigma average is equal to sigma x plus sigma y divided by 2, and I will rewrite this equation, sigma x minus sigma, sorry, plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 into cos of 2 theta plus tau of xy sine of 2 theta. So this will cancel with this, and we will get minus tau of xy into sine of 2 theta is equal to sigma x minus sigma y divided by 2 cos of 2 theta. Again we need tangent of theta, so you have to divide cos of theta on both hand side, so it will be equal to minus tau of xy tangent of 2 theta will be equal to sigma x minus sigma y divided by 2. So again this will be equal to tangent of 2 theta will be equal to minus sigma x minus sigma y divided by 2 tau of xy. Clear? And this theta will be equal to theta s, shear plane. So this will be the angle theta tangent of 2 theta s, where you will get the maximum shear stress, and it is this one. I have derived this in order to understand you. You can see here that it is written directly. So sorry. So you can see this is the same formula, tangent of 2s is equal to minus sigma x minus sigma y over 2 tau of xy. So if you have the value of sigma x, sigma y and tau of xy, you can easily find the shear plane. So at shear plane, the shear stress will be maximum. Along that shear plane, you will have the normal stress that will be equal to sigma average. Now this is one method to find out the shear plane. Clear? There is another method which is sigma s is equal to sigma p plus 45 degree. Why? So you can see this axis is, this x-axis is the normal stress. Clear? And this axis is shear stress. So you can see shear stress and normal stress are at a degree of 90 degree in Mohr circle, but actually it will be at a 45 degree. Clear? So that's why you can, if you know the shear plane and principal plane, clear, so you can easily find the shear plane as well. Clear? So you have two options. You can use this equation for finding the shear plane, or you have this equation for finding the shear plane. And at this point, at this shear plane, the shear stress will be maximum, that is equal to R, and normal stress will be equal to sigma dash, and that will be equal to sigma average. Now how you will represent these things? Remember that in our previous equation of shear plane, principal plane, this theta p comes out to be positive, and here shear plane the theta comes out to be negative. So as per book there is a convention that if the theta is in clockwise direction, clockwise, clear? So clockwise direction theta will consider as negative, and in counterclockwise direction theta will be taken as positive. So in this case you can see that if initial element was like this, there sigma x, sigma y, tau of xy, similarly this. So if you have find out the theta s, clear? So you will have to represent them on this. So this was initial x-axis and this y-axis. Now at theta s, for example theta s, here it is negative value, so we will go to the clockwise direction. So from this axis you will measure that theta s, clear? So this will be your x dash, and this will be perpendicular, you will be your y dash, clear? And you have to draw the element like this, clear? So on this phase this will be tau max, 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 and on this axis there will be normal stress, and that is equal to sigma average. Similarly on this y dash axis this will be sigma average, and similarly below this is sigma average. So what I have written over here is also available in this figure, clear? So this is now transform section, clear? I hope you have a clear picture of what is principal plane, what is principal stresses, what is maximum shearing stress, and what is shearing plane, clear? Now it will be further clear to you if you solve this example 7.01. So in this example you can see that an element that is experiencing a normal stress in this direction, that is 50 megapascal, that is tensile stress, and in y direction it is 10 megapascal, and that is compressive stress and shearing stress of 40 megapascal each. So we will write that sigma x is equal to 50 megapascal, clear? Sigma y is equal to minus 10 megapascal, and tau of x dash y dash is, now we will check. So you can see this is, as this phase is perpendicular to the axis, that is in positive direction, and the direction of force is in also positive y direction. So we can quickly say that this tau of xy will be equal to positive 40 megapascal. So you have these three values. So in question it is given that for the state of plane stress shown, determine the principal plane. So you have to find theta p. The part B is principal stress. Principal stress means sigma max and sigma minimum. And in part C it is given that maximum shearing stress and corresponding normal stress. So you have to find maximum shearing stress, and you know that at maximum shearing stress corresponding shearing stress is sigma x dash or sigma dash, and that is equal to sigma average. So let's start with the solution. First you will find the theta p, and theta p can be found by using this equation that we have derived earlier. Tangent of 2 theta p is equal to 2 tau of xy divided by sigma x minus sigma y. So from here you will get theta p, clear? Theta p1 and theta p2. We are not using Mohr circle, that's why we do not use 2 theta p1. You will get the answer here in term of 2 theta p2. So you have to divide them by 2 in order to get theta p1 and theta p2. Now the next step is to find out the maximum and minimum stress. So for maximum and minimum stress we have formula that is equal to sigma average plus minus r. So sigma average is this value and r is this one. So you have sigma x, sigma y, and tau xy all the values are present. So you have to just put the value and you will get sigma x and maximum and sigma minimum. The third portion is to find out the maximum stress. So maximum stress is equal to R, which is this. So you have to put the value and you will get the maximum shearing stress. Similarly, sigma dash at corresponding maximum shear stress is sigma x plus sigma y divided by 2. So when you put, you will get the answer. So you can see here, this is the solved problem. Clear? The problem is solved over here. So I think there is certain line that is from the start. Let me choose, they are not deleting. But you can see that this tangent of 2 theta p is equal to this. So top xy is 40, sigma x is 50 minus, and sigma y was minus 10. So when you solve this, tangent of 2 theta p will be equal to 1.33. And when you take theta, 2 theta p is equal to tan inverse of 1.33. So 2 theta p will be equal to 2 theta p will be equal to 53.1 degree, or it will be 53 plus 180, because in we see that 2 theta p2 is equal to 2 theta p1 plus 180 degree. That is in Mohr circle, but in normal routine or in this when you show it in elements, so 2 theta p2 is equal to theta p1 plus 90 degree. Clear? So if you add 180, so it will be, the next angle will be 233.1. Or if you convert 2 theta p, so theta p1 will be equal to 53 divided by 53.1 divided by 2, that will be equal to 26.6, and theta p2 will be equal to 90 plus 90, 26.6, and that will be equal to 116.6 degree. So it is written in here. So this is how we can find the principal plane. Now we will move toward determining the principal stress. So this is the equation of principal stress. When you put the value of sigma x, sigma y and tau xy, so you will get one value which is plus, that is 70 megapascal, and when you take a negative, so it will be minus 30 megapascal. So this is maximum normal stress and this is minimum. So initially the element was this. Now the stress has been transformed. Clear? So how you will find it? So initially this is x-axis and this was y-axis. Now we have find out that at angle of 26 plus 26. So at 26 degree, for example, this is 26.6 degree. So this will be the new transform x-axis dash, and this will be the y dash. So you have to draw the elements like this. So you can see at this angle, so normal stress in x direction will be equal to sigma max. Clear? You have to draw it neat and clean and according to your foot or ruler. Clear? And sigma y will be, or sigma minimum will be in y direction. That will be equal to sigma minimum. Also there is at principal plane, there will be principal stresses and no shear stresses. So this will be the answer, or this will be the element that is transformed. Okay, so sigma y is negative value. Sigma minimum is minus 30. So correct it. The direction will be, sigma y will be in this direction, not in tensile. So sigma x will be tensile and sigma y, which is sigma minimum, which will be the compressive stress. Clear? And there is no shear force at this angle, so we did not represent the shear force. Now the third was calculate the maximum shear stress. So maximum shear stress can be calculated by using formula tau max is equal to R, and R is this. Clear? So if you put the value, so tau max is 50 megapascal. Now you can also find theta s, 2 theta s is equal to 10 inverse. What was the formula? Kindly look, check it. This is the formula. minus sigma x minus sigma y divided by tau of xy minus sigma x minus sigma y divided by 2 tau of xy. So when you put the value, you can also calculate the shear angle, or you can see that shear plane is equal to theta p. We have written for plus 45 minus 45 is, but it depends again on the situation or scenario. Clear? So you can see that this theta p was in theta p. What was theta p? Theta p was 26.6 degree. So in counterclockwise, so again if you move toward clockwise direction, so you have to subtract it, or you can also use plus sign, but it will be clear to you in a next few lectures. So theta s, so now in this scenario I will advise you to use this formula to calculate theta s, because it will give you either plus or minus value. So theta s is equal to theta p minus 45. So if theta p is 26 point something, that we theta p1, so theta s1 will be this one, and theta s2 will be equal to theta p2 minus 45. Clear? So if you use theta p1 over here, you will get theta s1 is minus 18.4 degree, and if you use theta p2, which was 116. Clear? So when you use 116, so 116 minus 45 is 71.6, and the corresponding stress at this point at maximum shear stress is sigma x dash, which is equal to sigma average, and when you put the value, sigma x is 15, sigma y is minus 10 divided by 2, so sigma average is 20 megapascal. Now initially it was the initial x-axis, so now when you rotate the element at theta p, either minus 18.4, clear, and you will draw the element, so at that you will only show the maximum shear stress, that is 50 megapascal, and the normal stress will be the sigma dash, which is 20 megapascal. So you have transformed. You can also take 71.6. So what is that? You have this angle is 71.6 degree, but again that depend on the scenario. So either take minus 184 point, so definitely the remaining angle will be 71.6. I hope it's clear to you now. Now the next problem is sample problem 7.1. So this is very interesting problem. You can see that a single horizontal force P of 150 pound magnitude is applied to end D of lever ABC. So this is lever ABC, and at point D a 150 pound force is applied. Clear? So you have to determine the normal and shearing stress on element at point H having side parallel to X and Y. So let me zoom it. So you can see this is point H. So at point H, if these sides are parallel to X and Y, so you have to draw the normal and shearing stress on the element. It means that you have to show the sigma X, sigma Y on the element, and tau of XY. Clear? And second part is the principal plane. Why these things are coming to next slide? Don't know. Okay. The second part is the principal plane and principal stresses. So you have to find theta P1 and theta P2, and principal stresses sigma max and sigma minimum. So before solving this, you can see that this is at point D there is a force P is applied. So you have to represent them at this point. Clear? So this point when you move this point P to this point. So you can see this point P is producing a torque in the about y-axis, and this torque is equal to P. This torque is equal to P into this perpendicular distance 18. So this is torque about y-axis. Now you can also see that this torque, this point P is also producing a moment about x-axis. So moment about x-axis. Clear? So you can see that if we take this element and we applied this, there is a shear force on this. There is a force we have transformed. When we transform or we move this force to this point P, so there will be a moment about x-axis. Clear? And there will be a torque T about y-axis. So the solution is that determine an equivalent force coupled system at the center of transverse section passing through H. So you have to determine the force and coupled system, then evaluate the normal and shearing stress at H, and then at last we will find the principal plane and calculate the principal stresses. So let's move forward. So you can see here that this force is now transformed to this point H. Clear? But with a moment about x-axis, and this moment is 1.5 kips and a torque is 2.7 kips. Why? This torque is, when you multiply P with 18, P is 150 and 18, so this torque will be having some value that is written in next slide, and this moment about x-axis will be P into perpendicular distance, that is this 10. Clear? So that is shown in this next slide. So we have replaced the force with a force coupled system at the center. Clear? So the stresses and couples and torques are available over here. So this force is maximum at this point. Clear? And this force will be minimum at this point, because we know that the force will be maximum at the outer and minimum will be there. Now from our previous lectures in bending, we have discussed that whenever you have a beam and you applied, and this beam having a length in x direction, and that is applied by a load of y in y direction, or if you applied the beam with a movement, so it will bend. Clear? And there will be bending moment or bending stresses in y direction. So due to this mx is equal to 1.5 kips into inch, we have normal stresses in y direction. So as we know that sigma y is equal to mc over I, so this is moment about x-axis, this is the center from radius, so radius of this will be this one, and I think the radius is of this rod is given as 1.6 inch, 1.2 inch, and if the diameter is 1.2 inch, so radius C will be equal to 1.2 divided by 2, it will be equal to 0.6 inch. So, and I you can also calculate. So let's see that P is equal to 150, torque is equal to 150 multiplied by 18 that I have written earlier, and that is equal to 2.7 kips and into inch, and this moment was 150 into 10, that is 1.5 kips into inch. So all the values are shown over here. So now you can see that due to this moment x, moment about x, we have sigma normal stresses in y direction, and that is equal to mc over I. Now you have mm is 1.5 kips, c is the radius from center, that is 0.6 inch, and I for this circular tube or rod, not tube, or I for this circular rod is 1 over 4 pi c4. Clear? So when you put the value, you will get sigma x y. And the sigma y comes out to be 8.84 ksi. Now due to this torque, the shear stress is equal to T into C divided by J. So due to this torque, shear stresses will be generated in this rod, and this shear stresses torque xy is equal to Tc over J. T is the torque, C is the radius, and J is the polar moment of inertia for this circular shaft, and that is equal to pi by 2 into C4, and C is 0.4 inch, 0.6 inch. So when you calculate it, the tau of xy comes out to be tau of xy or tau of yx comes out to be 7.96 ksi. Also there is no stress in x direction, so sigma x will be 0. So when you represent it in the form of element, so this is the element, so there is no stress in x, so sigma x will be equal to 0, or it is better not to mention the stress in x direction because it is 0. Sigma y is 8. Sigma y is equal to 8.84 ksi. Clear? This is sigma y. And tau of xy or tau of yx will be equal to tau of yx. Tau of xy is equal to 7.96 ksi. So the part 1 is being solved to find out the stresses at point H. Now we will move toward the second part, that is find out the principal plane and principal stresses. Now you have sigma y, sigma x is 0, tau of xy, and you know that tangent of 2 theta p. To find out the principal plane, tangent of 2 theta p is equal to 2 tau of xy divided by sigma x minus sigma y, and when you put the value, this will be equal to minus 1.8. Tangent of 2 theta p is equal to minus 1.8, and 2 theta p is equal to tangent inverse minus 1.8 will give you two value. One is minus 61.0 degree, and other is when you add plus 180, because this is 2 theta p. So when you add 180 plus this value, so the other angle will be 119. Or if you take theta p, so theta p will be equal to 61 divided by 2, which is 30.5, and this 119 divided by 2 is 59.5. So this is the theta angle through which when we rotate the element, it will give you the normal stresses. Now what will be the maximum stresses or principal stresses? Now what will be the principal stresses? So sigma max comma sigma minimum is equal to this formula, sigma average plus r. So you have all the values sigma x, sigma y, and tau xy. So when you put it, you will get sigma max is equal to 13.52 and sigma minimum is equal to minus 4.68. So it means that this, let's say this was the original x-axis, clear, and this was the original y-axis. So if I rotate this element, so angle is minus 30.5. This is not a Mohr circle, so you will take theta p angle, so minus 30 theta p. So your x-axis will be mu x dash will be at a distance of theta p1, which is equal to minus 30.5 degree, and your y-axis will be this one. Again this angle will be equal to theta p1. Here this is y dash. So if you draw the element like this, you have to draw carefully. There. So you can see that this stress will be sigma max, and sigma max is, and this stress will be sigma max, and sigma minimum is negative, so it will be a negative sigma minimum, and this will be minimum. So you can see this is shown over here, this is point H, this is sigma max, again here it is shown, and this is sigma max, sigma minimum, sigma, and this is theta p angle. I hope you have enjoyed the second part of our chapter number 7. This was all about stress transformation. In our part 1st and part 2, we only discussed the stress transformation using transformation equation. Up till now, we have solved, we have derived out the equation of normal stress transform shear stress, and we did find the principal planes. We find out the principal stresses, that is, we find out the maximum shearing stresses along with its normal stress, and we find out the shear plane. Clear? And we solve the problem by using this knowledge. In our next lecture, we will move toward solving the problem using Mohr circle. So how you will deal with the given problem by using Mohr circle. And this Mohr circle is very interesting topic, and you will easily solve the stress transformation problems by using Mohr circle very easily as compared to these formulas, because in this you have to remember the formulas. So in Mohr circle you will be able to solve the question of stress transformation very easily. So stay tuned for the lecture, part 3 of the lectures, and if you like my videos, kindly subscribe, like and watch. Thank you.